Hello guys, welcome back to another video on my YouTube channel. I hope you enjoyed the last video. It was about, the volume and surface area of an n-dimensional hypersphere of radius 1. And it had lots of gamma functions. In this video, I want to be a little more technical. I'm actually going to state and derive the first Barnes lemma. And in the next video, I aspire to prove the second Barnes lemma. But before we do that, we're going to need the mellintransform. And I think this is a very good video to introduce that. Many people have, time and again recommended I use the mellintransform for various integrals on my channel. But, I needed a good overview, a good theory heavy video to actually be confident while implementing them. So with all that being said, let's get started. Okay, so we have first the definition of the Mellin-transform. So the Mellin-transform of f, which we can write as this weird m of, in curly brackets, f of x of s. I think that I should close the argument here. Which we can also, it's a function of s, right? So we can express that as a g of s. We can say that's some g of s. So therefore, the definition is integral 0 to infinity x to the s minus 1 f of x dx, such that, well, g is the Mellin-transform of f. And when it comes to choosing an s, we want an s such that the integral actually exists. So we want some s, some, inequality in s, sort of like the Laplace transform, whereby this integral converges. Otherwise, there's no way of really making sense of this. Now, interestingly, if we set f of x equal to e to the minus x, then g of s, the Mellin-transform of f of x, is going to be the gamma of s, just purely from definition. And the condition that we need for this to equal the gamma function, the Mellin-transform to equal the gamma function, is that the real part of s has to be greater than 0. Okay, fair enough. We have g of s equals integral 0 to infinity e to the s minus 1 times ln x. I'm just expressing x to the s minus 1 as an exponential raised to some factor times ln. We can write this as e to the ln of x to the s minus 1. Using log properties, we can multiply by the power of the x beside the natural log on top, times f of x dx. What help does that do? We can set x equal to e to the minus u dx minus e to the minus u du. And then we have g of s equal to integral from minus infinity to infinity, using the substitution we had, e to the u times 1 minus s, f of e to the minus u du. Okay, so far it's just standard procedure, and now we can simplify a few things. The exponentials will cancel, the u dependences will go away. There'll only be an su dependence. So integral from minus infinity to infinity, e to the minus su, f of e to the minus u du. Now we can just change s, which was earlier some complex variable, to be I times omega, where right now let's say omega is real. So we're just fixing s to be purely imaginary. And we can again change the variable of integration from u to t, because it's a definite integral. It's fine, we can do that. So we have g of I omega equals integral minus infinity e to the minus I omega t, f of e to the minus t dt. Now this form of the integrand here should feel familiar to you. Well, it is indeed the Fourier transform of f of e to the minus t evaluated, or the output variable is omega. Now the output variable, writing it like that is important, because look at the variable, the argument on the left hand side. We have I omega and we have omega here. So there's some sort of, relationship between that. And again, g of I omega is basically just the Mellin transform of f of t evaluated at I omega, because that's how we basically defined it on top. Okay, fair enough. So we have these two sets of relationships between the Mellin transform and the Fourier transform. So we have the Mellin transform of f of t if as a function of omega is the Fourier transform of f of e to the minus t as a function of negative I omega. And similarly, we can invert this around to have the Fourier transform of f of t as a function of omega is the Mellin transform of f of negative natural log of t as a function of I omega. So these are two nice properties. We also are going to need one more property for the next part of this, I guess, discussion about Mellin and Fourier transforms. So the Mellin transform of f of t, but now instead of just having some purely real omega, we're gonna not only multiply an I to the omega, but also add another a. Now a is again a real number, so a plus I times omega. So we're just complexifying the argument on in the first equation. When I do that, I'll just get the change like that on the right hand side. So the Fourier transform of f of e to the minus t as a function of minus ia plus omega. And now, since we've complexified what the the frequency is, the omega, or the the final output of the Fourier transform is, this is simply the modified Fourier transform. And if you recall, when we needed this, when the poles of the Fourier transform function, which was a function of omega, lay on the real axis. That's when we had to either jump around the pole or shift the entire contour up and down by introducing an imaginary component to our frequency. Now we can use the shift theorem in Fourier transforms. So if we have Fourier transform of a function as the output, where the output variable is minus ia plus omega, we can write that as the Fourier transform of the function, which in this case is f of e to the minus t times e to the negative of whatever term we had here. So that's going to get e to the minus at of omega. Okay. This is a standard property. I won't really prove it in this video. I think I have proven this in one of the older videos I made for the Math YouTuber challenge. Please check that out if you haven't. And it's pretty straightforward to prove. It's just plug this in the definition, change the variable, and Bob's your uncle. Okay. So let's actually try to invert it, because Mellin transform is good, but we also care about the inverse of transformations, be it modified Fourier, or Laplace, and in this case the Mellin transform as well. Let's start with something we know, the Fourier transform. So Fourier transform of f of t as a function of omega is integral minus infinity to infinity of e to the minus I omega t f of t dt, which we can also denote as f cap as a function of omega. Now, this notation might be a little confusing. We're using this curly f with the parentheses, and we're also using this cap notation. But I think this sort of, helps us illustrate the point even more, that the final output Fourier transform is only a function of omega. It doesn't really care what the variable of integration was. This could be t plus a for all you care. Okay. And its inverse, obviously. And since we're considering the modified Fourier transform later on, we will have to ensure that the omega avoids the poles. The omega in this case would, be complex. So f of t is 1 over 2 pi integral minus infinity to infinity e to the I omega t f cap of omega d omega. This is the inverse Fourier transform. Okay, if we choose the function h of t equals f of e to the minus t times e to the minus at, then we have f e to the minus at times f of e to the minus t, which will be on the left hand side now, equals, now we're just writing the inverse of this function, of the Fourier transform of that. So 1 over 2 pi integral minus infinity to infinity e to the I omega t times the Fourier transform of the function h, which I will call h cap of omega d omega, where h cap is appropriately the Fourier transform of f of e to the minus t e to the minus at as a function of omega. And now we can just use the relation that we derived, the latest relation that we have here. So if we have Fourier transform f of e to the minus t e to the minus at as a function of omega, we can just replace that by the Mellin transform of f of t, evaluate as a function of a plus I omega. So I'm just doing that here. And I'm gonna introduce a change of variables. So a plus I omega, well, it's a complex number. A is real, omega is real. And let's call that s a complex number. ds is d omega over I. So we have e to the minus at f of e to the minus t equals 1 over 2 pi I, and that should be suggestive to you. Integral from a minus I infinity to a plus I infinity e to the s minus a times t times the Mellin transform of f of t as a function of s ds. Now I'm going to call the Mellin transform of f of t as a function of s as capital F of s. This is sort of in alignment with the cap notation for the Fourier transform. I want to emphasize that we don't care what the variable of integration was, because we've integrated over it. That part's done. All we care about is the output s, especially since we're integrating over s inside. So let's introduce another change of variables. So t goes to minus ln t, and since this is not a variable of integration, we don't really need to care about the ds, the differential element. And that also does not affect the t inside the Mellin transform f of t, because that f of t has already been accounted for. That integral has been performed, and we've already obtained a Mellin transform, which is a function of s. So that way, that t is really not going to affect the f of t. The only t it affects, apart from the one on the left hand side, obviously, is the one that's inside the integral as a part of the integrand. So we can simplify few things, use the property of the natural log and exponents. We get t to the a f of t equals 1 over 2 pi I integral a minus I infinity to a plus I infinity t to the minus I omega capital F of s ds, which, we can just rearrange this. So we can take the a to the right hand side. So we get t to the minus a minus I omega. Now a plus I omega is s, so that just becomes t to the minus s f of s ds, and everything else is the same, including the 1 over 2 pi I and the range. And all that just equals f of t. So we have a mechanism of, from integrating a Fourier transform of f of t, we can by plugging that Fourier transform inside an integral and performing some integration with some prefactor, we're actually getting f of t back. So that means that this entire thing should be the inverse Mellin transform of capital F of s as a function of t, right? Because we plugged the Mellin transform in, and it exactly undid the Mellin transform. Capital F of s was a Mellin transform of f of t, small f of t. And, that's exactly what we're getting on the left-hand side. And we need to be careful what a is. Well, let's see what a was. A was the real part of s. What was s? S was this complex number designation that we had on this complex frequency, which, should look like a modified Fourier transform to you. And that's exactly how we, get this inverse, by basically just relating this with the modified Fourier transform. So A is just the real part of S. And what about the convergence? Well, we know what S is based on, the initial Mellin transform, As I said, the S should be in a good range so that the integral converges. But what's also important is when we're integrating over the S, we don't want to have any poles on that vertical line. So since this is going to be a vertical line, right? Unless you sort of deviate, more or less, you can deform it to a vertical line once you fix the A in a good place. But that A should be placed in such an area where there's no poles of the function inside, which is capital F of S. Because if that happens, capital F of S blows up and the integral does not converge. So the region of convergence is important, just like in modified Fourier transforms and by extension Laplace transforms. And the main thing is to avoid the poles. You get a condition from, the initial convergence of the Mellin transform, and you get the criteria that you have to avoid the poles as well, because we want everything to be defined. Okay, moving on, and here are some examples. Now we know that the Mellin transform of e to the minus t is the gamma function, so we can just invert this using the inversion formula that we have. E to the minus t is 1 over 2 pi I integral a minus I infinity to a plus I infinity t to the minus s gamma of s ds. You can also derive this from going from the right hand side to the left hand side using the residue theorem, and that's why the 2 pi I was suggestive. But you just need to know where the poles of the gamma function are and what their nature is. Are they simple, or do they have multiplicity 2 or greater? And that is actually going to be covered a little further in this video. Another nice Mellin transform we have is the 1 over 1 plus t squared Mellin transform, which evaluated to pi over sine of pi s over 2. You can get this as sort of a relation between gamma functions that gives the reflection formula. And this is also a very nice integral. Again, we can go from the right to the left by just knowing where the poles of the sine are. In this case, they're going to be even integers. And we can just do the infinite sum and the infinite residue theorem for the infinite poles that it has, and arrive at this answer that we have, with, of course, the right choice of A. Okay, moving on now. That was the recap. This is what we really are going to need. So consider the following Mellin transform. I is integral 0 to infinity t to the lambda of divided by 1 plus t to the lambda. And then, of course, we have t to the s minus 1. That was the customary factor in the Mellin transform integral. So the Mellin transform function that we're going to evaluate is t to the lambda over 1 plus t whole to the whole lambda. Simple variable change, t plus 1 goes to t. We have integral 1 to infinity t minus 1 to the lambda plus s minus 1 divided by t to the lambda dt. Another change, t goes to 1 over t. So integral I is 0 to 1, 1 minus t to the lambda plus s minus 1, t to the minus s minus 1 dt, which is, if you compare to the standard form of the beta function, beta of minus s, comma lambda plus s. And we can use the relation from the beta to gamma. This is gamma of lambda plus s, gamma of minus s divided by gamma of lambda. And this is the Mellin transform of this function. So we can just invert this now, again using the the right a values and everything. So we have t to the lambda over 1 plus t whole lambda equals 1 over 2 pi I times 1 over gamma of lambda integral a minus I infinity to a plus I infinity gamma of lambda plus s gamma of minus s t to the minus s ds. Now, what about the region of convergence? That's a good question. So in this part, there doesn't seem to be too much of a problem. The main thing we need to check is the Mellin transform we got. That Mellin transform has gamma functions, and does the gamma function have any poles, if at all, and what are they? Because at those values of S, our right hand side is going to blow up. That means that the Mellin transform is not defined, and that's clearly outside the range of the S. So for that, to know the poles of the gamma function, we can just take the Weierstrass definition of the gamma. Gamma of z is e to the minus Euler-Mascheroni times z over z. And the product from 1 to infinity of e to the z over k divided by 1 plus z over k. Now notice that if we take the limit as z goes to n for n equals 0, minus 1, minus 2, so basically all the non-positive integers, then the gamma will blow up because, there's these factors of z and 1 plus z over k in the denominator. But if you take limit as z goes to n of z minus n times gamma of z, well, that converges because that, factorizes one of the factors that were annoying for us. For again, n equals 0, minus 1, minus 2. So that means we have poles of order 1 for the gamma at the values z equals 0, minus 1, minus 2, also known as simple poles. That's nice. Simple poles are nice to work with, and we really like them. So therefore, the Mellin transform of t to the lambda over 1 plus t whole lambda as a function of s is gamma of minus s, gamma of lambda plus s over gamma of lambda. And the poles of the gamma function, gamma of minus s, using this this property is 0, 1, 2, dot, dot, dot. So all non-negative integers. Poles of lambda plus s are at s equals minus lambda, minus 1, minus lambda, minus 2. And whenever we're integrating, we're going to choose the real value of the s. We're going to have to avoid these poles. So be sure to have your real part of s not lie on any of these poles of either gamma of minus s or gamma of lambda plus s. And this is a more of a specific case. If the real part of lambda is greater than 0, that means we can there's a space between the negative lambda, real part of negative lambda, and 0. Just place your s in between them. Just place your real part of s, between both of them. Because with this condition, we're guaranteeing there's a space between minus lambda and 0. And the standard choice, and again, this is just the standard choice. You can, basically choose any a value where you're avoiding any of these bad poles. But this is the more standard choice because you get a more wider window rather than just one integer worth of window. So the standard choice is to put a equals the real part of s between the real part of minus lambda and 0. Okay, fair enough. So, when that happens, our a is between the real part of minus lambda and 0. So if we have a blue line of integration along which, the real part of a is well within this standard region that we've chosen for the real part of lambda greater than 0 condition, we can always deform this. So basically take a to be infinitesimally small, infinitesimally close, to the point that we can deform it to almost be on the imaginary axis, just skirting off of that imaginary axis and then jumping off the pole because the pole is at 0 for the gamma of minus s. So the gamma of minus s poles are actually ascending, and the other gamma, lambda plus s, are actually descending. So the condition that we have of real part of lambda greater than 0, that sort of allows a separation. We can place the contour between the separation of the poles that allows for some nice breadth between these the sequence of ascending and descending poles, and this is a concept that we're going to use throughout this video. Now moving on, we have this formula in yellow from the inversion of the function we Mellin transformed. So let's take t equals a over b. So we have 1 plus 1 over a plus b to the lambda equals 1 over 2 pi I times 1 over gamma of lambda. And now I can, since I've chosen a standard location for the real part of S, which is a, I can just remove that from now on and assume that, because that's the standard choice. So integral minus I infinity gamma of minus s gamma of s plus lambda b to the s over a to the lambda plus s ds. And again, I'm emphasizing that this implies that we've chosen the appropriate real part of s contour such that it avoids the poles, and if real part of lambda is greater than 0, then we're choosing as much as possible the standard place to place the real part of s, that's between real part of minus lambda and 0. Now this is known in literature as the Mellin-Barnes integral and has lots of applications. Notably, the most famous application is in quantum field theory. Now I never thought I was going to actually indirectly talk of some kind of quantum field theory in this YouTube channel of mine. But here we are, and that's really the beauty of mathematics and physics going in hand. So if we have a scattering process or an interaction process whereby either one particle enters point X, interacts, or in the sense it breaks down and then exits as a changed particle at Y, say it has a interaction path, so that's one particle, that can be one particle decay, or you can have two particles where you have to reverse or the direction of the arrow, or just take a negative momentum on the Y segment, where two particles are colliding, and then these A interaction paths are basically the different possible interactions between them. In quantum field theory, we care a lot about the possibilities of every process. So if we convert this Feynman diagram, this is a Feynman diagram, into mathematical integration, something that can be computed, all of these paths are going to be contributing a term which is given by gf of x comma y. This is called the Feynman propagator. So we take the limit as epsilon goes to 0, 1 over 2 pi to the fourth, because we're in 4 dimensions, integral over the 4 momentum, so d4 of p, e to the ip x minus y, where this is the 4 momentum product. So if you're in Minkowski, you would have that Minkowski signature, divided by p squared minus m squared plus I epsilon, the whole thing to the a power, where m is actually the rest mass that's in the kinetic term of your Lagrangian scalar expression. I'm again assuming this is a scalar field theory just for simplicity's sake. So using our Mellin-Barnes integral, we can write the 1 over p squared minus m squared to the a, and we have a because there's a of these interaction paths. We have 1 over gamma of a times 1 over 2 pi I integral minus I infinity to I infinity dz gamma of a plus z gamma of minus z times minus m squared to the z divided by p squared to the a plus z. This is nice because not only is this integral easier to work with, but it also helps us sort of do an energy comparison, because we care about values of the magnitude m squared over p squared, or its reciprocal, when we're actually doing these high energy theoretical physics calculations. Okay, fair enough. That's the end of that application. And again, if you don't understand something, don't fret, this is just a small application. If anyone, is well versed in quantum field theory, they would understand and appreciate it. If you don't, it's fine. Okay, so the first Barnes lemma, this is the result I promised at the start of the video. Now we've built up all the machinery. We've built up Mellin transforms, the Mellin inverse transforms, and we've also have the Mellin-Barnes integral, or also known as the Mellin-Barnes representation, either one you choose. Okay, so the Barnes lemma, let's state it, says that 1 over 2 pi I integral minus I infinity to I infinity dz of gamma of alpha 1 minus z, gamma of alpha 2 minus z, gamma of beta 1 plus z, gamma of beta 2 plus z, all of that equals gamma of alpha 2 plus beta 2, gamma of alpha 1 plus beta 1, gamma of alpha 1 plus beta 2, gamma of alpha 2 plus beta 1 divided by gamma of alpha 1 plus alpha 2 plus beta 1 plus beta 2. Now that's a mouthful. People consider this to be the generalization of the relation between the beta function and the gamma function, because that's what this right hand side looks like. Now, anyways, we want to care about what contour of integration we should choose, because again, I'm suppressing the a here, assuming that we're in a good range, in a standard sort of choice. So now we know from just looking at the integrand that the poles of the gamma are at alpha 1 or alpha 2 or alpha 1 or alpha 2 plus 1, so on. So we just keep adding integers to either alpha 1 or alpha 2. So I'm just writing that as alpha I, where I is going from 1 to 2. That's the ascending poles, and the descending poles are minus beta j minus 1 minus beta j minus 2, where again j is holds for 1 and 2. So for both beta 1 and beta 2, we have descending poles. So we are ascending and descending poles. The condition we need here, again, like the nice condition, the standard choice in the Mellin-Barnes integral, the condition is that the real part of alpha I plus beta j is greater than 0 for all ij, where I and j both go from 1 to 2 independently, such that we can place the real part of z, and z is the integration variable instead of s this time, such that we can place the contour, which is the real part of z, between this wide window of the real part of alpha I and the negative real part of beta j, where for all ij. This basically sort of follows, instead of lambda, we just have an alpha I plus beta j now for all ij. That's all that's changed. And that's why, because of this condition, we can actually find width to place our contour inside, and that will actually segregate the ascending poles on the right side and the descending poles to the left side. So we've again managed to separate them out. Because of this condition, we could make a standard choice like that. Now, this is just a standard choice. In fact, you can relax this condition, where the condition will just say that the real part of alpha I plus beta j is not a negative integer or 0, which basically means you're avoiding all the poles, which is kind of common sense. But that then you may not be able to make such a standard choice. You can make some non-standard choice, which is fine, should give you the same thing. But I think there's a certain elegance to this condition and this choice, as you'd see. And again, this alludes to Laplace transforms, where we had a nice wide window for the S. So the left-hand side for the first Barnes lemma, is integral minus I infinity to I infinity dz over 2 pi I gamma of alpha 1 minus z, alpha 2 minus z, gamma of beta 1 plus z, gamma of beta 2 plus z. And again, we're assuming this condition is a given in this entire proof. So assume that real part of alpha I plus beta j is greater than 0 for all ij. Again, we have the standard range of minus real part of beta j less than real part of less than real part of alpha I for all ij. Let's use the definition of the integral definition now of the gamma function. So gamma of alpha is integral 0 to infinity dt t to the alpha minus 1 e to the minus t. And this holds for a real part of alpha greater than 0. In other way, this is just the Mellin transform of e to the minus t, as we learned in this video. We're going to use this definition for gamma of alpha 1 minus z and gamma of beta 1 plus z. Now, alpha 1 and beta 1 are arbitrary choices. We could have taken any two pairs. We could have taken alpha 1 beta 2 or alpha 2 beta 2. It doesn't matter because this condition holds for all ij. So we're not going to really run into any problems with the convergence, and therein lies the elegance of that stricter requirement, as I said. So we just have these last two guys. This sorry, not the last two, but the first gamma and the third gamma being replaced by this integral from 0 to infinity. So we have two of those integrals for both of them, and we're actually pulling them outside. They're actually inside the integral from minus I infinity to I infinity. We're pulling them outside. I'm going to justify why we can do that in a few lines. But so what happens is this is the t1 is just the first alpha 1 minus z gamma function integral representation. Similarly, the t2, I'm not going to bother enunciating each term. And the other terms are the two other gamma functions from minus I infinity to I infinity, dz over 2 pi I, gamma of alpha 2 minus z, gamma of beta 2 plus z. We can actually get the z dependent terms inside the infinity integral, the I infinity integrals. Okay, so we have integral 0 to infinity dt1 t1 to the alpha 1 minus 1 e to the minus t1, integral 0 to infinity dt2 t2 to the b1 plus 1 e to the minus t2, and finally the integral to minus I infinity to I infinity dz over 2 pi I times t2 over t1 whole thing to the z, and times gamma of alpha 2 minus z, gamma of beta 2 plus z. Now, this is the justification why we can do that. Interchange of integrals is possible. Pulling the 0 infinity out, the t1, t2 integrals outside from the z integral is because the gamma function, again evaluated at an arbitrary complex number x plus iy, only thing is y goes to infinity. This is fine because our integral bounds were from minus I infinity to I infinity. The interchange is possible because we see that the gamma can be approximated using the Stirling formula by square root 2 pi product x plus iy to the x plus iy e to the minus x plus iy x plus iy to the minus 1/2 in absolute value, which is approximated as square root 2 pi e to the minus absolute value y pi over 2 absolute value y to the x minus 1/2. Now, if you want more details about this derivation, it's just a little shorthand approximation going on, and little complex analysis and complex arguments and all those things. All of this holds as long as absolute value y goes to infinity. So we see it's actually bounded because infinity was the only case that was really troubling us. So you can actually see that it's really bounded. It's really bounded, and it's going to decay because of this exponential term and not going to oscillate. If x goes to infinity, it actually oscillates. Okay, and that we can use dominated convergence theorem to argue that we can interchange the integrals. Now, you might say, well, Stirling formula is only for, some natural number n, because it was for the factorial and gamma is just the extension of the factorial. And here we have a complex number. Well, the thing is, there's a more general proof of the Stirling's formula using Laplace's method of steepest descent. I may make a video on that. Let's see. But this formula basically exists, the asymptotic formula for the gamma function. So now recall this formula we had. 1 over a plus b to the lambda equals 1 over 2 pi I times 1 over gamma of lambda integral minus I infinity to I infinity gamma of minus z prime, now integration variable z prime, gamma of z prime plus lambda, b to the z prime divided by a to the lambda plus z prime dz prime. Set lambda to be a2 plus b2. So we have 1 over a plus b to the a2 plus b2 equals 1 over 2 pi I times 1 over gamma of a2 plus b2, integral minus I infinity to I infinity, gamma of minus z prime, gamma of z prime plus alpha 2 plus beta 2, b to the z prime divided by a to the alpha 2 plus beta 2 plus z prime dz prime. Change the variable, z prime equals z minus alpha 2. Before we do that, let's see what the condition of convergence was. Well, we know from the beginning, the central assumption we started this lemma with, that the real part of alpha 2 plus beta 2 is greater than 0, because 2 also comes in the for all ij condition. So that means the real part of z prime can be placed in that nice standard choice that we had for the Mellin-Barnes integral. So minus real part of alpha 2 plus beta 2 is less than real part of z prime is less than 0. This is the standard choice. Since real part of alpha 2 plus beta 2 is greater than 0 from the first condition, we can make this standard choice. And that will actually help us, because when we change the variables, going from the z prime to the z, we actually end up with the original condition. Minus real part of beta 2 less than real part of z less than real part of alpha 2. That's the only condition we need. And that condition is already considered in the bigger condition that we used to start this proof. And that's nice, because in this integration that we were doing in yellow here, we had an integration variable z, which was already supposed to satisfy that condition. So whatever I talked about right now is basically trying to evaluate what this rightmost integral is, and the z fits the bill. The integration variable in the end that we need actually fits the bill, because it satisfies the original condition. And that's why I like this elegance in that condition. So we have gamma of alpha plus beta, b to the alpha 2, a to the beta 2 divided by a plus b alpha 2 plus beta 2. Integral minus I infinity to I infinity dz over 2 pi I, b over a to the z, gamma of alpha 2 minus z, gamma of beta 2 plus z. Please pardon if I keep changing from the physicist notation for the integral differential to the mathematician, because sometimes it's more convenient when you have lots of long integrals to use the physicist notation. They mean the same thing, obviously. So the left hand side becomes, because now we can just replace, we know what the rightmost integral was on top, right? We just have to change the b value that we had and the a value that we had. So b is t2 over here and a is t1, and we just know what this is using the Mellin-Barnes integral that we actually computed before in white, and then did a variable change and parameter change as well. So that's going to be gamma of alpha 2 plus beta 2 divided by t1 plus t2 to the alpha 2 plus beta 2 times t2 to the alpha 2, t1 to the beta 2, and everything else is the same. It's basically just an integral over t1 and t2. It's all the same as before. We can pull out the constants. So gamma of alpha 2 plus beta 2, integral 0 to infinity dt1, integral 0 to infinity dt2, t1 to the alpha 1 plus beta 2 minus 1, t2 to the alpha 2 plus beta 1 minus 1 divided by t1 plus t2 to the alpha 2 plus beta 2 e to the minus t1 plus t2. And we're almost done. It's just a little bit of multivariable calculus now, meaning we have to change the variable. So t1 is eta times epsilon and t2 is eta times 1 minus epsilon, where eta and epsilon are the two new variables. We need two new variables going from 2 dimensions of t1, t2 to 2 new dimensions of eta and epsilon. The Jacobian is epsilon n eta, 1 minus epsilon negative eta, the determinant of which is negative eta epsilon minus negative eta times 1 minus epsilon, which is negative eta. But we need the absolute value of the determinant. The orientation doesn't matter. if we, you know, if we orient it in a natural way, in the sense that instead of going from like 1 to 0, if we had gone, we're going from 0 to 1 and 0 to infinity for each d, for d epsilon and d eta respectively. So the integral is now gamma of alpha 2 plus beta 2, integral from 0 to infinity d eta, eta to the alpha 1 plus beta 1 minus 1, e to the minus eta, integral 0 to 1 d epsilon, epsilon to the alpha 1 plus beta 2 minus 1 minus epsilon, alpha 2 plus beta 1 minus 1. And this range of integration can be found simply by just considering each inequality. The inequalities that we consider are t1 greater than or equal to 0, t2 greater than or equal to 0, and we get a bunch of inequalities for eta and epsilon. So this first guy, this leftmost integral, is actually just the gamma of alpha 1 plus beta 1, and the last integral is just the beta function of alpha 1 plus beta 2 comma alpha 2 plus beta 1. And we have the prefactor of gamma of alpha 2 plus beta 2. We can combine everything and, you know, write the beta as in terms of the gamma functions using the famous relation. Gamma of alpha 2 plus beta 2, gamma of alpha 1 plus beta 1, gamma of alpha 1 plus beta 2, gamma of alpha 2 plus beta 1, all divided by gamma of alpha 1 plus alpha 2 plus beta 1 plus beta 2, which is precisely the right hand side of the first Barnes lemma. And I shall end this video here. There's actually a second Barnes lemma also, which is way more complicated, and I think I should dedicate fresh video to that, because I already spent a lot of time, you know, explaining the mellintransform and the inversion and all sorts of things about the convergence. But I hope you saw the elegance in that condition we chose. You know, it popped up a bunch of times. It's very self-consistent. That's why I like you know, well-defined things in analysis specifically. Please apologize. I apologize for any problems, any you know, misspeaking I may have done. If I maybe call a Laplace transform a Mellin transform, or a Mellin transform a Laplace, or either a Fourier transform, I'm sorry for that. It's just hard, you know, to remember and talk of these things as dynamically when you're, you know, explaining. But I hope you understood a lot and learned a lot from this video. So see you in the next one, hopefully, for the second Barnes lemma. Peace out.